Hello, my name is Elena Zotova. I am a researcher at Vicomtech and I'm going to present the participation of the Vicomtech NLP team at the task MEDDOPROF on behalf of my colleagues Aitor and Montse. MEDDOPROF Shared Task includes 3 tracks. The first track is named entity recognition, where we should detect mentions of occupations in clinical text. The goal of the second track is to categorize occupations as patient, a family member, a health professional, or someone else. And the third track is the normalization task. Its goal is to map the first task prediction to one of the codes in a list of the unique concept identifiers. These identifiers are related to professions, labor activities, and occupations from SNOMED clinical terms, and European skills, competences, qualifications, and occupations classifications. Both SNOMED and ESCO are thesaurus with an ontological foundation. We present systems for 3 tracks. All of them leverage transformer architecture in different forms. Our end-to-end joint model tackles all 3 tasks. Besides, we present 2 systems for the normalization task. One of them is based on sequence-to-sequence transformer architecture, and the other is based on the idea of semantic similarity. The joint model is implemented as a regular sequence labeling task. We have token embeddings as input and labels as output of the model. At the core, there is a pre-trained BERT model that encodes the text. And the normalization task is solved with the hierarchical classification approach. The system solves all 3 tasks and it is trained simultaneously. First, we encode the text with BERT model. All tokens are converted into contextual word embeddings, and these embeddings are the base for several classification heads, 1 head per task. We experimented with 2 pre-trained models, BEDO and ISHA-M-BERT. BEDO model performed better in our validation set. The joint model also deals with the normalization task with a hierarchical classification approach. The hierarchical classification is a bunch of classification heads, 1 per each non-terminal node. In the ESCO ontology, the first digit is the most coarse-grained category. Each following digit adds a more fine-grained definition. So the key difference with a flat classifier is that we build a tree of chords, level by level. Each node of the tree has a limited number of children nodes. Non-terminal nodes are turned into classifiers that predict the digit of the next level according to the hierarchy. At inference time, the final code is reconstructed starting by the prediction of the root node until reaching a leaf. This approach is computationally expensive. We need about 800 classifiers for it. The second approach we present for the normalization task is self-attention transformer architecture. Term description is a source input for the encoder, and its code in the ontology is an input for the decoder. This system is implemented with the OpenNMT framework, broadly used for neural translation tasks. Here we see the parameters of the neural network, 6 encoder layers and 16 attention heads. This combination was selected as a result of various experiments. For this system, we prepare a training corpus. The set of valid codes from the ontologies consists of more than 3,000 unique codes. Some of them have synonymous definitions. We split them and assign a corresponding code to each synonym. You can see a sample of the corpus in the table. Next, we combine the training set of the normalization task and the description of all codes and obtain more than 15,000 examples for the training. We also reserve 10% of our original training set as a development set. On preprocessing steps, the source sequences are lowercase, cleaned from punctuation, and tokenized on word level. The target codes are just tokenized by space. The output of the model is a sequence of symbols that can be interpreted as a code from ontologies. This approach has some advantages. First, it turns an extremely large multi-class classification problem into a straightforward sequence-to-sequence approach. The model learns to translate terms to codes directly. Second, pairs of codes and their descriptions are already defined in ontologies, so we leverage them as extra training data. The semantic mapping system is based on the idea of semantic search. So we use a previously detected term as query. Our ontologies are the collection of documents to search in, and the cousin similarity is the measure of relevance between the term and its definition. The codes are separated by synonyms, so each code has various descriptions. We have experimented with different pre-trained language models to create common vector space for terms and code descriptions, and selected the LabSE model as the best performing. LabSE is a BERT sentence embedding model supporting more than 100 languages. Since the type of a term is detected in a previous task, we experiment with the search collection. One system searches in SNOMED, CITY, and ESCO separately, and the second system searches in the database when both ontologies are united. For the case of the separate search, we select the closest description with the condition depending on the tag assigned previously. In our experiments, mapping of SNOMED codes obtained a micro F1 score of 57.7 and ESCO codes obtained 21.5. So the performance of the semantic search method depends on the number of target elements. The performance of the multitask joint model is reasonably good for name entity recognition and classification task, as you can see in this table. The F scores are 25 and 31% above the baseline, respectively. For the normalization task, the best performance system is a model with sequence-to-sequence approach. Nevertheless, the score, even for the best system, is below the baseline score. Since in the normalization task input is the output of the previous task, the error accumulation lowers the final score. That is all. If you have any question, please do not hesitate to ask them. Here you have our emails, and thank you very much for your attention.